There is a quiet fact that almost everyone gets wrong about the beginning of the universe. The Big Bang was not an explosion that happened somewhere far away. It happened everywhere at once, including the exact spot where you are resting right now. The space your bed sits in was part of it. Tonight, we will walk slowly through what the Big Bang actually was, and the many things it was not, including why there is no center, why there was no sound, and why physics still falls silent when we ask what came first. Before we begin, I would love to know where in the world you are listening from, and what the clock happens to say where you are. Leave it in a comment if you like. I find it lovely to picture all the quiet rooms these slow words drift into. And now, let your shoulders fall, and let us begin. Take a breath. There is nothing here you need to solve. Nothing to memorize, nothing to keep up with. The whole point of the next couple of hours is to move very slowly through a very large idea, the way you might walk through a museum late at night when all the other visitors have gone home and you have the long, quiet halls entirely to yourself. We are going to take the single biggest event we know of, the beginning of everything, and we are going to turn it over gently in our hands, one small piece at a time. If your mind drifts, that is fine. If you fall asleep before the end, that is more than fine. That is rather the idea. You can always come back tomorrow and pick up wherever you left off, and the universe will still be exactly as patient as it was the night before. So settle in. Let the weight of the day start to leave your arms and your legs. We have plenty of time, and I am in no hurry at all. Let me begin somewhere very ordinary, because the strangest ideas almost always have an ordinary doorway. Think for a moment about the last time you stood outside on a clear, dark night, far enough from streetlights that the sky opened up properly. Maybe it was on a holiday somewhere quiet, or on a walk you took alone, or simply a night when you happened to look up at the right moment. You saw stars, of course. Thousands of them if the sky was dark enough, scattered across the black like grains of salt spilled on a table. And if the night was very clear, you might have noticed a faint pale band stretching from one side of the sky to the other, a soft river of light. That band is the Milky Way, the flattened disk of our own galaxy seen edge-on from the inside. Now here is the gentle thing to hold on to. Every single point of light you saw that night is old. The light left those stars long before it reached your eyes. Some of it left when dinosaurs were still alive. Some of it left before the sun and the earth even existed. When you look up at the night sky, you are not seeing the universe as it is. You are seeing the universe as it was, layered in time, like rings in a very old tree. And the further out you look, the further back in time you are looking. This simple fact, that looking out into space is the same as looking back into the past, is the thread we are going to follow all the way back to the beginning. Because if you keep looking further and further out, keep peeling back the layers, you eventually reach the oldest light there is. And that light has a story to tell about how everything started. Let us sit with that for a moment before we go any further. Light is the messenger. The further it has traveled, the older the news it carries. And there is a piece of light, the oldest of all, that has been traveling toward us since almost the very beginning, carrying the oldest news there is. Here is a second ordinary doorway, one you have felt with your own skin. Think about a cup of tea, freshly poured, sitting on the table beside you. When you first make it, it is hot. Steam rises. And then, slowly, with no effort on anyone's part, it cools. The heat spreads out into the room and is lost. By morning, the cup is stone cold. This is one of the most reliable things in the entire universe. Heat always spreads out. Hot things cool. Concentrated energy disperses. Nothing stays hot forever on its own. And this simple truth, the cooling of a cup of tea, turns out to be one of the most important clues we have about the beginning, because the whole universe is, in a sense, an enormous cup of tea that has been cooling for nearly 14 billion years. It started searingly hot, and it has been cooling ever since, and we can still feel the faint warmth of how hot it once was. Hold on to that cup of tea. We will come back to it. So here's the question we are circling tonight, and I want you to feel the shape of it before we try to answer it. What was the Big Bang? Not the cartoon version, with a single bright flash going off in the middle of empty darkness. The real thing. Where did it happen? When did it happen? What banged? And what did it bang into? And the deeper you push on those questions, the stranger they become, because almost every word in them turns out to be slightly wrong. There was no middle. There was no darkness around it, waiting to be filled. There may not even have been a where in the way we usually mean it. The honest truth is that the Big Bang is one of the most misunderstood ideas in all of science, partly because the name itself is misleading, and partly because the reality is so far outside anything our hands have ever touched. Tonight, we are going to take all of that misunderstanding apart, slowly, kindly, and put something truer in its place. To do that properly, we have to go back about 100 years to a time when nobody knew any of this. And I mean nobody. As recently as the early 1920s, the most respected astronomers in the world were not even sure whether other galaxies existed. Let me take you there. Picture the world in the year 1920. The First World War has only just ended. There are no satellites, no computers as we know them, no space telescopes. Astronomy is done by men and a few women sitting in cold domes through the night, guiding heavy telescopes by hand and capturing starlight on glass photographic plates. And the great debate of the age, the one that fills the journals and the lecture halls, is deceptively simple. When you look up and see those faint, fuzzy, spiral-shaped smudges of light that the astronomers call nebulae, what are they? Are they clouds of gas inside our own Milky Way, which many believed was the entire universe? Or are they separate islands, vast collections of stars so far away that they appear only as smudges, each one a galaxy in its own right? The whole question of how big the universe is hung on the answer. This was such a serious and unresolved question that, in April of 1920, the leading astronomers of the day held a famous public discussion about it, which has come to be known simply as the Great Debate. It took place in Washington at the Smithsonian, and it set two respected astronomers against each other. On one side stood Harlow Shapley, who argued that the Milky Way was the entire universe, a single vast system of stars, and that the spiral nebulae were merely clouds within it. On the other side stood Heber Curtis, who argued that the spirals were separate galaxies, distant island universes in their own right, each one comparable to our own. Both men were thoughtful. Both had evidence. And at the time, nobody could say for certain who was right. The matter simply could not be settled with the data they had. It would take a bigger telescope and a few more years, and the patient measurement of those faint, pulsing stars before the answer became clear. I tell you this so that you can feel how genuinely open the question was. We so easily imagine that the size of the universe was always obvious. It was not. A little over 100 years ago, the wisest people alive did not know whether the universe was one galaxy or countless galaxies. That is how recently we have learned almost everything we know. One of the quiet figures in this story worked at the Lowell Observatory. on a hill above Flagstaff in Arizona. His name was Vestos Slipher, born in 1875. A careful and unhurried man who spent years doing something most astronomers had not thought to do. He took the light from those spiral nebulae and spread it out into its colors, the way a prism spreads sunlight into a rainbow. When you spread starlight out like that, you find dark lines crossing the rainbow at specific places, like missing teeth in a comb. Those lines are fingerprints. They tell you which chemical elements are present in the star, because each element absorbs light at its own particular colors. And here is the part that mattered. Slipher noticed that in many of these nebulae, the whole pattern of lines was shifted, pushed toward the red end of the rainbow, as if the entire fingerprint had slid sideways. Now, a shift like that has a meaning. When something that emits waves moves away from you, the waves it sends get stretched out, and stretched out, light looks redder. You have heard the sound version of this your whole life, even if you never named it. When an ambulance races past you, the pitch of its siren drops the instant it passes and begins moving away. The sound waves get stretched. Light does the same thing. So when Slipher found that the light from these spiral nebulae was shifted toward red, he was seeing the signature of motion. And what he found, measurement after patient measurement through the 1910s, was that nearly all of them were moving away from us, and many were moving away astonishingly fast, faster than anything anyone had measured before. He did not yet know what it meant. He had simply found, very quietly, one of the most important clues in the history of science, and most of the world was not paying attention. While Slipher was measuring redshifts in Arizona, a young mathematician in Russia was looking at the same universe from a completely different direction, with nothing but a pencil and Albert Einstein's equations. His name was Alexander Friedmann, born in 1888 in St. Petersburg. Friedmann was not an astronomer. He never looked through a great telescope searching for the answer. He was a mathematician and a meteorologist, a man who had flown in balloons to record the weather and who thought in equations the way other people think in pictures. And in the early 1920s, he did something bold. He took the brand new theory of gravity that Einstein had published in 1915, the general theory of relativity, and he asked it a simple, enormous question. What does this theory say about the universe as a whole? Einstein's theory described gravity not as a force pulling across empty space, but as a kind of bending. Matter tells space how to curve, and the curve of space tells matter how to move. It was a beautiful and difficult idea, and Einstein himself, when he applied it to the entire cosmos, had assumed the universe must be eternal and unchanging, the same size forever. It simply seemed obvious. The stars had always been there. The universe was the stage on which everything happened, and stages do not grow or shrink. To make his equations agree with that unchanging picture, Einstein had even added a special term, a kind of cosmic pressure he called the cosmological constant, just to hold everything still. It is worth pausing on how reluctant Einstein was, because it tells you something about how deep this assumption ran. Here was the man who had overturned our entire understanding of space and time, who had shown that the universe was far stranger than anyone imagined. And yet, even he could not bring himself to believe that the universe might change in size. The idea of an unchanging cosmos was so deeply woven into human thought that it felt less like a theory and more like plain common sense. So Einstein reached into his own equations and inserted that extra term, the cosmological constant, a kind of invisible push spread evenly through all of space, finely tuned to exactly balance gravity and keep the universe from either collapsing or expanding. It was, by his own later admission, an awkward and inelegant fix. added not because the physics demanded it, but because his expectations did. Years afterward, once the expansion of the universe had been confirmed, Einstein is reported to have called the cosmological constant the biggest blunder of his life, regretting that he had not simply trusted his original equations, which had been quietly trying to tell him all along that the universe could not sit still. Whether he used those exact words is debated by historians, but the regret was real enough. He had been so close to predicting the expansion himself, and his own certainty had held him back. Friedman did not make that assumption. He let the equations speak for themselves. And when he did, in 1922, they told him something that nobody wanted to hear. The natural state of a universe full of matter, according to Einstein's own theory, was not to sit still. It was to move. It could expand, growing larger with time, or it could contract, falling inward. What it almost certainly would not do was nothing. A static universe, Friedman showed, was like a pencil balanced perfectly on its tip. Possible in theory, but the slightest nudge would send it one way or the other. Einstein, when he first read this, did not like it at all. He even published a short note claiming Friedman had made an error, and then later, quietly, had to withdraw that note and admit the younger man's mathematics was correct. Friedman had found the expanding universe years before anyone had proof of it. Tragically, he never lived to see it confirmed. He died in 1925, only 37 years old, from typhoid fever, his great insight still little more than a curiosity in a journal. And now we come to the man at the very heart of this story, a man you may never have heard of, which is itself one of the small injustices of history. His name was Georges Lemaitre, born in 1894 in the Belgian city of Charleroi. Lemaitre was two things at once that people rarely expect to find in the same person. He was a Catholic priest, ordained and devout, and he was a serious physicist who had studied at Cambridge in England and at Harvard and the Massachusetts Institute of Technology in the United States. He wore the collar of a priest, and he did mathematics that would reshape our entire picture of existence. And he saw absolutely no conflict between the two. In 1927, working largely on his own, Lemaitre arrived at the expanding universe from the equations, much as Friedman had, though apparently without knowing of the Russians' work at first. But Lemaitre went one crucial step further. He connected the mathematics to the sky. He knew about the red shifts that astronomers like Slipher had been measuring, those galaxies sliding away into the red. And he put the two halves together. If the universe is expanding, he reasoned, then galaxies should appear to rush away from us, and the more distant ones should rush away faster, in direct proportion to their distance. He even worked out, from the data available to him, roughly how fast that expansion should be. He published all of this in 1927 in a Belgian scientific journal in French, and almost nobody read it. The journal was obscure, the language was a barrier, and the idea was simply too strange. His great paper sank like a stone, and for a couple of years the most important idea in cosmology sat unnoticed on a library shelf. Then came the telescope and the man who made the discovery undeniable. Edwin Hubble was born in 1889 in Missouri. He had been a boxer, a lawyer, a soldier, and a school teacher before he gave himself fully to the stars. And he had a flair for the dramatic that the quiet Slipher and the gentle Lemaitre entirely lacked. Hubble worked at the Mount Wilson Observatory in the mountains above Los Angeles, and he had at his disposal the most powerful telescope on Earth, the 100-inch Hooker telescope, named for its main mirror, which was 100 inches across. With that great eye, in the years around 1923 and 1924, Hubble settled the old debate once and for all. He found, Inside the great spiral nebula in the constellation Andromeda, individual stars of a special kind, stars that pulse with a steady, measurable rhythm, brightening and dimming on a regular schedule. These pulsing stars are called Cepheid variables, and they are one of the most useful tools astronomers have ever found, thanks to a woman whose name deserves to be said aloud. Henrietta Swan Leavitt, born in 1868, worked at the Harvard College Observatory as one of a group of women hired to examine photographic plates, paid very little, and given almost no recognition at the time. Working through plate after plate in the years around 1908 to 1912, Leavitt discovered something remarkable about these pulsing stars. The slower they pulse, the brighter they truly are, and the relationship is precise. This means that if you measure how slowly a Cepheid pulses, you know its true brightness. And if you know its true brightness and compare it to how dim it looks from Earth, you can calculate exactly how far away it is. Leavitt had handed astronomy a ruler that could measure the cosmos. She died of cancer in 1921 at only 53 and never received the recognition she earned. But it was her ruler that Hubble used. When Hubble measured the distance to those Cepheids in Andromeda, the answer was staggering. They were far, far outside the Milky Way. Andromeda was not a cloud in our own galaxy. It was a separate galaxy entirely, an island of billions of stars, almost unimaginably far away. In a single stroke, the universe had become vastly, dizzyingly larger than anyone had dared to believe. There was not one galaxy. There were countless galaxies, scattered through a space so large the mind simply slides off it. And that was only the first of Hubble's gifts. Because then Hubble, working with his assistant Milton Humason, a former mule driver and janitor at the observatory who had taught himself to become a superb observer, did the thing that ties this whole story together. They measured the distances to many galaxies using Leavitt's ruler, and they compared those distances to the redshifts, the speeds at which the galaxies were rushing away, the very speeds Slipher and others had recorded. And in 1929, Hubble announced the result. The relationship was exactly what Lemaitre had predicted and what Friedman's mathematics had implied. The farther away a galaxy is, the faster it is receding. Double the distance, and you double the speed. It held galaxy after galaxy, a clean straight line on the graph. There is a small piece of historical fairness worth mentioning here, because this story has more than its share of people who did the work and missed the credit. For most of a century, the relationship between a galaxy's distance and its speed of recession was known simply as Hubble's law, named for the man at the great telescope who measured it and announced it to the world. But as we have seen, Georges Lemaitre had derived that very relationship and even estimated the rate of expansion 2 years earlier. In his overlooked 1927 paper written in French, he had simply published it quietly in an obscure journal, in a language few of the leading astronomers read, and the world passed it by. In 2018, nearly a century later, the International Astronomical Union, the body that speaks for astronomers worldwide, voted to recognize this. The relationship is now properly called the Hubble-Lemaitre law, carrying both names, the famous astronomer and the quiet priest, the telescope and the equations, side by side at last. It is a small thing, a change of name in the textbooks. But there is something fitting about it, a debt acknowledged after a long time. And I like to think Lemaitre, who never seemed to mind much about credit and went on teaching and thinking until his death in 1966, would have allowed himself a small, private smile. The universe was not static. The universe was expanding. Everything was flying apart. Now, Let us slow right down here, because this is the moment where most people form a picture in their heads that is wrong, and it is so easy to do. And once it is there, it is hard to shake loose. So let me give you the wrong picture first, gently, and then take it apart. The wrong picture goes like this. There was a point in space. The point exploded like a firework or a bomb. Bits of matter flew outward in all directions into the empty space around them. And those bits became the galaxies, still flying outward to this day. And we are sitting on one of the fragments. It is a very natural picture. It is also almost entirely mistaken. And the reason it is mistaken comes down to one word that we have to handle very carefully tonight. And that word is space. When the galaxies fly apart, they are not flying through space like shrapnel through air. The space between them is itself growing. That is the heart of it, and I am going to say it several times tonight in several different ways, because it is the single idea that everything else hangs from. The galaxies are not moving apart. The space between them is expanding, carrying them along with it. Let me give you the analogy that astronomers have used for nearly a century, because it really is the best one. Imagine a loaf of raisin bread dough sitting in a warm kitchen, slowly rising. The raisins are scattered through the dough, here and there, near and far. Now the dough begins to rise. As it expands, every raisin moves away from every other raisin. If you were a tiny creature sitting on one particular raisin, you would look around and see all the other raisins moving away from you. And here is the lovely part. The raisins that started out far from you would appear to move away faster because there is more dough between you and them, and all of that dough is expanding at once. The raisins close by would drift away slowly. The distant ones would race off. That is precisely what Hubble saw in the galaxies. The far ones recede faster than the near ones. But notice the thing the analogy makes obvious. No raisin is at the center. Sit on any raisin you like, and every other raisin moves away from you, and you will feel as though you are at the middle of the whole thing. But you are not, because there is no middle. Every raisin sees the same view. The expansion is not happening from a point. It is happening everywhere, throughout the entire dough, all at once. The dough itself is growing. The raisins are just going along for the ride. So when a galaxy far away shows a large redshift, that light has not been stretched because the galaxy is speeding away through space like a thrown ball. It has been stretched because the space the light has been traveling through grew while the light was crossing it. The light set out one color, and over millions or billions of years, the very space it was passing through expanded underneath it, stretching the waves longer and redder by the time they reached your telescope. The redshift is not really about motion at all, in the everyday sense. It is about the swelling of space itself. Let me make sure this distinction is really clear, because it is one of those places where people nod along and then realize, a moment later, that they have lost the thread. When the ambulance races past you and its siren drops in pitch, the sound waves are stretched because the ambulance is moving through the air, away from you. That is one kind of stretching, the everyday kind, caused by something physically traveling away. But the stretching of light from distant galaxies is not quite that. The galaxies are not, for the most part, hurtling through space away from us like the ambulance through the air. Most of them are sitting more or less still in their own patch of space, just as the raisins sit still in the dough. What is moving them apart is the growth of the space in between. And as that space grows, any light crossing it is stretched along with it. Not because the source is fleeing, but because the very medium the light travels through is swelling. It is a deeper and stranger kind of stretching than the ambulances. And it is the reason astronomers are a little careful about the word speed when they talk about very distant galaxies. The most distant galaxies are receding from us faster than light itself could travel, which sounds impossible and would be impossible if they were truly moving through space. But they are not. It is the space itself that is expanding between us, and space is permitted to do things that objects within it are not. Do not worry if that last point slips away from you. It slips away from nearly everyone. The single thing to keep as you drift is this. The redshift is the fingerprint of stretched space, not of objects in flight. This is one of the deepest and most beautiful ideas in all of science, and most people carry around the firework version their whole lives instead. So hold on to the bread. The dough is rising. The raisins are coming along. There is no center, and nothing is exploding into anything. There is only space, quietly and relentlessly growing. Let me offer you a second version of the same picture, because some people find one easier to hold than the other, and it is good to have both. Imagine the surface of a balloon, not yet fully inflated, with small dots drawn all over it in marker pen. The dots are the galaxies. Now imagine slowly blowing the balloon up. As the rubber stretches, every dot moves away from every other dot. Pick any dot and watch from its point of view, and all the other dots recede from it. The dots themselves do not crawl across the surface of the balloon. They stay exactly where they were drawn. It is the surface between them that stretches, carrying them apart. And once again, there is no special dot, no central dot, no dot that the others are fleeing from. Every dot sees the same thing. The expansion belongs to the surface itself, not to any point on it. Now, the balloon picture invites a question that almost everyone asks. And it is a wonderful question. So let us take it seriously. If the universe is expanding like the surface of a balloon, then what is it expanding into? Surely it must be getting bigger inside some larger empty space, the way a real balloon swells into the air of the room. And here is the subtle and rather mind-bending answer. There may be no larger space for it to expand into. In the balloon picture, we are only allowed to think about the surface of the balloon, the thin skin, and not the air inside or the room outside. Those do not exist in the analogy. For a creature living on the surface of the balloon with no concept of inside or outside, the surface is everything there is, and it is simply getting larger. There is no edge to reach and no outside to expand into. The expansion is not the universe growing into something else. It is space itself, all the space there is, becoming more of itself. That is genuinely hard to picture, and if it makes your mind slip, that is completely normal. Nobody pictures it easily. The mathematics describes it perfectly well, but our imaginations, shaped by a lifetime of watching things expand into rooms, were simply not built for it. So do not strain. Just let the strangeness be strange. The universe does not expand into anything. It is all there is, and there is steadily more of it. And here is something that follows, which surprises many people. The universe might be infinite. It might have no edge and no boundary, going on forever in every direction. If that is the case, then it was always infinite, even at the very beginning. An infinite universe does not start as a tiny dot and grow. Rather, it starts infinitely large and extremely dense everywhere, and then becomes infinitely large and less dense everywhere, as everything spreads apart. When we say the early universe was small, what we really mean, if the universe is infinite, is that everything was packed close together. that any 2 points you might pick were much nearer to each other than they are today. The whole infinite expanse was hot and dense, not squeezed into one location, but crowded together everywhere at once. Or the universe might be finite, curved around on itself like the surface of that balloon, so that if you traveled far enough in a perfectly straight line, you would eventually return to where you began, having gone all the way around without ever hitting a wall. We do not yet know which of these is true. Our measurements tell us the universe is very close to flat, which leaves both possibilities open. It is one more honest gap in our knowledge, sitting quietly alongside the others, and there is no shame in it. The universe is under no obligation to be easy for us to picture. Now, here is the thought that follows, and it is the thought that gives us the Big Bang. If the universe is expanding, if everything is getting farther apart as time goes forward, then run the film backward. Imagine playing the whole history of the universe in reverse. The galaxies, instead of rushing apart, would draw together. The space between them would shrink. Everything that is spread out would crowd inward. And the further back you wind the film, the closer together everything gets, and the denser and hotter it becomes, until you reach a moment, very far back, when everything we can see was packed into an unimaginably small, hot, dense state. That is what we mean, at its simplest, by the Big Bang. Not a bang in empty space. The earliest moment we can sensibly talk about, when the entire observable universe was compressed together and almost inconceivably hot. This was Lemaitre's great leap, and it is worth pausing on it. He was the first to take the expansion seriously enough to follow it backward all the way. If everything is flying apart now, he reasoned, then long ago it must all have been together. He called this beginning the primeval atom, sometimes translated as the primal atom or the cosmic egg. He imagined the whole universe beginning as a single dense entity that, in some sense, came apart, unfolding into all the matter and space we see. He published this idea in 1931. And here is something I find quietly moving. A Catholic priest, working out the equations of physics, was the first human being to seriously propose that the universe had a beginning, a definite starting point in time, rather than stretching back forever. He himself was always careful to keep his science and his faith in separate rooms. He insisted that his primeval atom was a scientific idea to be judged by evidence and not by scripture, and when others tried to use it to prove religious claims, he gently but firmly objected. He wanted the physics to stand on its own. Now I should be honest with you about how strange and unwelcome this idea was at first, because it helps explain one of the great confusions, the very name we are using. Many physicists in the 1930s and 40s hated the notion of a beginning. It felt almost unscientific to them, too sudden, too much like a creation story dressed up in equations. They preferred a universe that had always existed and always would. And the loudest of these skeptics was a brilliant British astronomer named Fred Hoyle. Born in 1915, a man of fierce intelligence and even fiercer stubbornness, Hoyle, together with Hermann Bondi and Thomas Gold, developed a rival theory in 1948 called the steady-state model. In their picture, the universe was expanding, yes, but it had no beginning. As galaxies moved apart, new matter was continually created in the gaps, very slowly, just enough to keep the overall density of the universe the same forever. The universe always looked roughly the same. It had no birth and would have no death. It simply was, eternally. And here is where the name comes from. In 1949, Fred Hoyle was giving a talk on the radio, on the British Broadcasting Corporation, explaining the different theories of the cosmos to the public. to describe Lemaitre's idea of a sudden dense beginning, the idea he himself did not believe in. Hoyle reportedly used a vivid, dismissive phrase. He called it, with a certain scorn, this Big Bang. He meant it to sound crude, almost silly, a cartoon of an idea compared to his own elegant, eternal universe. And the name stuck. It stuck so well that the theory Hoyle was mocking is now known across the world by the very phrase he coined to belittle it. There is a small lesson in that about who gets to name things, and about how the universe does not much care what we call it. Hoyle himself, late in life, insisted he had not meant the phrase as an insult, only as a striking image for the radio. Whatever he intended, the name is a poor one, because as we have seen, it was not big in the sense of happening at a place, and it was not a bang in the sense of making a sound. There was no air to carry sound. There was no outside to hear it. Let us linger on that, because it is one of the most common quiet confusions of all. People hear the word bang and naturally imagine a noise, a great cosmic boom rolling across the heavens. But sound is a very ordinary, very physical thing. Sound is a wave of pressure traveling through a material, through air or water or stone. When you speak, you push on the air, and the air pushes on the air next to it, and that ripple of pressure travels until it reaches an ear. Without a material to carry it, there can be no sound at all. And in the beginning, there was no air, no surrounding medium, nothing outside the universe through which any sound could travel. So whatever else the Big Bang was, it was utterly silent, in the way that all of space is silent, a silence so complete that the word silence almost fails to capture it. And then there is the other half of the name, the word bang itself, with its suggestion of an explosion, something blowing apart and scattering debris outward into the space around it. But there was no space around it for debris to scatter into. There was no outside. The Big Bang was not a thing happening at a place within a larger emptiness. It was the beginning of the place itself, and of the time itself, expanding from within, with nothing outside and no sound and no flash seen from afar. Two small words, big and bang, and both of them point in exactly the wrong direction. It is a wonder anyone understands the idea at all, given the name we hung on it. But you, lying here tonight, now understand it better than most. It did not bang. It did not happen anywhere in particular. It happened to everywhere, all at once, in perfect silence. And in a sense it is happening still, gently, in the space all around you. But the name endures, and we are stuck with it. And so we keep explaining, patiently, that the words mean almost the opposite of what they sound like. Now, you might reasonably ask, if both theories existed, the Big Bang and the steady state, how did we ever decide between them? Two clever models of the universe, each defended by serious scientists. How does anyone settle a question that large? And the answer is one of the most wonderful stories in the history of science, and it begins, of all places, with a horn-shaped antenna in a field in New Jersey and a pair of pigeons. But before we get to the pigeons, I have to tell you about a prediction, because the prediction came first, and the people who made it were largely ignored, which seems to be a recurring theme in this story. In the 1940s, a Russian-born physicist named George Gamow, who had fled the Soviet Union and settled in the United States, became fascinated by the early universe. Gamow, born in 1904, was a large, jovial, mischievous man, famous for his sense of humor as much as his physics. He reasoned that if the universe had truly begun in an extremely hot, dense state, then in those first minutes it would have been a kind of cosmic furnace, hot enough to forge the lightest chemical elements out of raw particles. Working with two younger physicists, Ralph Alpher and Robert Herman, Gamow began to calculate what that early furnace would have produced. Now, Gamow could not resist a joke. When he and Alpher wrote up their first major paper on this in 1948, Gamow noticed that the names Alpher and Gamow sounded like the Greek letters alpha and gamma, the first and third letters of the Greek alphabet. So he playfully added the name of another famous physicist, Hans Bethe, in the middle, purely so that the paper would be authored by Alpher, Bethe, and Gamow, alpha, beta, gamma. Bethe had little to do with the work, but cheerfully went along with the joke. It is remembered to this day as the Alpha Beta Gamma paper, and it is one of the foundation stones of our understanding of how the universe made its first elements. Let me slow down and walk you through what that early furnace actually did, because it is one of the places where the Big Bang stops being an abstract idea and starts making concrete predictions that we can check. In the first moments, the universe was far too hot for atoms, or even for the centers of atoms, to hold together. It was a roiling soup of the most basic particles, the building blocks that would later assemble into everything. As the universe expanded and cooled, just as our cup of tea cools, it passed through a series of stages, each one possible only within a particular range of temperature, like a kitchen where different dishes can be cooked only at different heats. In the first second, the most basic particles settled out of the soup. Then, in roughly the first 3 minutes, something extraordinary happened. The universe had cooled just enough for the centers of the simplest atoms to begin sticking together, but it was still hot enough to fuse them, the same kind of fusion that powers the sun. In that brief window, only a few minutes long, the raw particles fused into the lightest elements. Mostly hydrogen, the simplest of all, a good deal of helium, the next simplest, and tiny traces of a couple of others. And then the window closed. The universe expanded and cooled past the point where fusion could continue, and the recipe was set. The proportions made in those first 3 minutes were locked in place. Here is why this matters so much. Physicists can calculate, from the theory alone, exactly what proportions of hydrogen and helium that early furnace should have produced. And then, astronomers can go out and measure the actual proportions of hydrogen and helium in the oldest, most pristine gas in the universe, gas that has not been much altered since the beginning. And the two numbers match. The amount of helium predicted by the Big Bang, about 1/4 of all the ordinary matter by weight, is just about exactly what we observe. This is one of the great, quiet triumphs of the whole theory. The recipe written in the first 3 minutes of existence is still legible today, in the composition of the stars and the gas between them, and it reads exactly as the theory said it should. When you breathe, the hydrogen woven into the water of your body, the hydrogen that helps make you up, was forged in those first 3 minutes. It is almost as old as time itself. Young Ralph Alpher, sadly, found his serious contribution somewhat overshadowed by the famous names attached for the joke, which stung him for the rest of his life. But the prediction that matters most for us tonight came from Alpher and Herman, also in 1948. They realized that if the early universe had truly been a furnace of light and heat, that heat would not simply vanish. As the universe expanded and cooled over billions of years, the original blaze of the beginning would still be out there, everywhere, but stretched and cooled by all that expansion into a faint whisper of radiation. They calculated, remarkably, that this leftover glow should still fill the entire universe today, cooled all the way down to just a few degrees above the coldest possible temperature, what we call absolute zero. They predicted a temperature of around 5 degrees above absolute zero. It was a stunning prediction, a way to actually test whether the Big Bang had happened. If the universe had begun in fire, the ashes of that fire should still be glowing, faintly, in every direction. And then, almost unbelievably, the world forgot about it. The prediction sat in the journals for 16 years, unnoticed, untested, while the debate between the Big Bang and the steady state rumbled on without anyone realizing that the deciding evidence had already been predicted and was simply waiting to be found. So now we come to the pigeons. In the early 1960s, at the Bell Telephone Laboratories in Holmdel, New Jersey, two young radio astronomers were given the use of a remarkable instrument. Their names were Arno Penzias, born in 1933, a refugee who had fled Nazi Germany as a child, and Robert Wilson, born in 1936, a quiet, meticulous Texan. The instrument was a large horn-shaped antenna, originally built to bounce radio signals off early communication satellites. It was extraordinarily sensitive, one of the best radio receivers in the world, and Penzias and Wilson wanted to use it to study the faint radio glow of our own galaxy. To do that, they needed to account for every possible source of noise in their equipment, every hiss and crackle, so that they could be sure any signal they found was real. And here is where their trouble began. No matter where they pointed the antenna in the sky, no matter the time of day or the season, they detected a faint, steady hiss, a persistent background noise that would not go away. It came from every direction equally. It did not rise or fall with the sun. It did not match anything in their galaxy. It was just there, a soft static, the same everywhere they looked. To good experimentalists, an unexplained noise is intolerable. It must have a cause. So they set about hunting it down. They checked every connection. They cooled their equipment. They considered radio interference from nearby New York City and ruled it out. And then they discovered that a pair of pigeons had been roosting inside the great horn of the antenna and had coated the inside with what the two men, in their published account, delicately described as a white dielectric material, which is to say, pigeon droppings. So they evicted the pigeons. They climbed inside and scrubbed the antenna clean. They sealed it up. And the hiss remained exactly as before, soft and steady and coming from everywhere. They were baffled. They had a signal they could not explain, a faint glow filling the entire sky at a temperature of about 3 degrees above absolute zero, and they had no idea what it was. They were on the very edge of one of the greatest discoveries in human history, and they did not know it. They thought they had a problem with their equipment. Meanwhile, just about an hour's drive away, at Princeton University, another group of physicists was working out, entirely independently, that the Big Bang should have left behind exactly such a glow. This group was led by Robert Dicke, a gifted physicist who, not knowing of Alpher and Hermann's earlier prediction, had reasoned his way to the same conclusion. The early universe was a furnace. The furnace left ashes. The ashes should still be glowing, faintly, everywhere, at a few degrees above absolute zero. Dicke had set his younger colleagues, including a brilliant young physicist named Jim Peebles and an experimentalist named David Wilkinson, to the task of actually building an antenna to search for this glow. They were, quite literally, in the middle of preparing to look for the very thing that Penzias and Wilson had already accidentally found. The two stories collided through a phone call. Penzias happened to mention his mysterious noise to another astronomer, who knew of the Princeton group's work and suggested he get in touch with Dicke. Penzias called Princeton. As Dicke listened to the description of the steady 3-degree hiss coming from every direction, he reportedly turned to the others in his office and said quietly that they had been scooped. Someone else had found it first, by accident, without even knowing what it was. Dickey and his group drove out to New Jersey to see the antenna and confirm the result. And so, in 1965, two short papers were published together in the same journal. One, by Penzias and Wilson, reported a mysterious excess of radio noise described in the cautious, careful language of people who do not want to overstate their claims. The other, by Dickey and his Princeton colleagues, explained what that noise actually was. It was the cosmic microwave background. It was the oldest light in the universe. It was the afterglow of the Big Bang itself, the cooled and stretched remnant of the fire of the beginning, still falling on the Earth from every direction in the sky after nearly 14 billion years. Let that settle for a moment. The faint hiss that those two men spent months trying to eliminate from their equipment, the noise they blamed on pigeons, was the echo of creation. It is, in a sense, the most important sound in science, except that it is not a sound at all, but a glow so faint and so stretched that it has slipped out of the range of visible light entirely and into the realm of microwaves. In fact, you have very likely seen it yourself, in a small way, without knowing, if you are old enough to remember the days of analog television. Before everything went digital, you may remember that when a channel had nothing broadcasting, the screen would fill with a snowy, hissing static. A small fraction of that static, a tiny percentage of those flickering dots, was the cosmic microwave background. The afterglow of the Big Bang was leaking into your living room, into your old television set, and was dismissed as nothing more than bad reception. The beginning of the universe, mistaken for static. There is something almost unbearably gentle about that. Now let me tell you exactly what that ancient glow is, because it is more beautiful and more precise than the word afterglow suggests. For the first several 100,000 years, the universe was not transparent. It was filled with a hot, glowing fog. It was so hot that atoms could not hold together. The centers of atoms and the tiny particles called electrons that normally orbit them were torn apart, drifting separately through a dense, charged haze, and light cannot travel freely through such a haze. The loose electrons constantly scatter light, knocking it this way and that, the way fog scatters the beam of a car's headlights so that you cannot see through it. So the early universe was opaque, a glowing fog through which no light could pass in a straight line. If you had somehow been there, you would have seen a bright, blank glow in every direction, like being inside a cloud lit from within. It is strange to imagine being present in those early times, and it is worth doing slowly, because it dissolves the firework picture better than almost anything. There was no darkness to stand in and watch an explosion across the sky. There was no sky, no across, no vantage point from which to observe. Everywhere was the same. If you could somehow have floated in the universe a single second after the beginning, you would not have seen a bright point off in the distance with darkness around it. You would have been immersed, on every side, in an even, blinding, featureless glow, hotter than the inside of any star, the same in every direction, with no edge and no center and no outside. There would have been no here and no there in any meaningful sense, because everywhere was packed close to everywhere else. The whole universe was the explosion, if you even want to use that word, and you were inside it, and so was everything else, with nothing left over to be the empty space it expanded into. This is the picture to keep. Not a bomb going off in a dark room, but a glowing everywhere, cooling and spreading and thinning, with no spectator and no stage. Then, about 380,000 years after the beginning, the universe cooled to a particular temperature, around 3,000 degrees, cool enough at last for the electrons to settle into orbit around the atomic centers and form the first complete neutral atoms. And in that moment, almost everywhere at once, the fog lifted. With the electrons now bound up in atoms, there was nothing left to scatter the light. And suddenly light could travel freely across the universe in straight lines, as it does today. The universe became transparent. And the light that was set free in that moment, the light that happened to be traveling when the fog cleared, has been traveling ever since, for nearly 14 billion years, stretched longer and cooler by the expansion of space the whole way, until it arrives now at your antenna, at your old television, at the roof of your house, as the faint microwave glow we call the cosmic microwave background. So when we detect that glow, we are not seeing the Big Bang itself. We are seeing the moment the fog lifted 380,000 years after the beginning. We are seeing the oldest light it is possible to see, because before that moment there was no light that could travel freely to be seen. It is a wall, in a sense, a wall of glowing fog beyond which we cannot look with ordinary light, no matter how good our telescopes become. Astronomers call it the surface of last scattering, the last place that ancient light bounced before flying free. When you look at a map of the cosmic microwave background, you are looking at a photograph of the universe as it was at 380,000 years old, the earliest baby picture there is, and every tiny ripple in it is a seed of everything that came later. Think for a moment about what it means to have a wall like that at the edge of everything we can see. It is not a wall made of brick or stone. It is a wall made of time and fog. Beyond it, the universe certainly continues, going back those last 380,000 years to the very beginning, but the light from that deeper past is locked away behind the glowing haze, unable to reach us as ordinary light. So no matter how large or how perfect a telescope we ever manage to build, there is a horizon of sight beyond which the ordinary light of the cosmos simply cannot carry us. And there is something restful in that, I think, rather than frustrating. We have walked all the way to the edge of what light can show us, and we have stood there, and we have taken the photograph. And the photograph is almost unimaginably old. Imagine standing at dawn in a valley filled with low morning mist, the kind that pools in the hollows of the land before the sun has fully risen. You cannot see the far side of the valley. The mist holds the light and softens it into a single pale glow. And then, as the air slowly warms, the mist thins and lifts. All at once it seems, and the far hills appear. And the light that had been trapped flows freely across the whole valley. The clearing of that early universe was a little like that morning, except that it happened everywhere at the same instant, in every direction, across all of space. And the light set free in that clearing has been traveling toward you ever since. The map we make of it is the oldest thing any eye or any instrument will ever see. And it is, in the gentlest possible sense, a portrait of the morning the universe became clear. With the discovery of that ancient glow, the great debate was effectively over. The steady-state universe, the eternal one with no beginning, had no good explanation for why the sky should be filled with the cooled radiation of a hot, dense early phase. The Big Bang did. Fred Hoyle, to his great credit, was a fighter who continued to defend and modify his ideas for the rest of his life. But the tide had turned decisively. Penzias and Wilson, the two men who found the glow without understanding it, were awarded the Nobel Prize in 1978. And so the picture seemed, for a time, more or less complete. The universe began hot and dense. It has been expanding and cooling ever since, and we can still see the afterglow. A clean story. Except it was not quite complete. Because the more carefully scientists looked at that afterglow, the more they ran into puzzles that the simple version of the Big Bang could not explain. And it is here, in these puzzles, that some of the deepest confusions and some of the most honest uncertainties begin. So let us slow down again, settle a little deeper into the quiet, and walk into the strange parts. The first puzzle is this, and it is a beautiful one. When astronomers measured the temperature of the cosmic microwave background in different directions, they found something almost too perfect. The glow coming from one side of the sky was at the very same temperature as the glow coming from the exact opposite side of the sky, to an astonishing precision, agreeing to better than 1 part in 10,000. The whole sky glowed at the same gentle warmth, about 2.7 degrees above absolute zero, no matter which way you looked. And at first that sounds reassuring, even unremarkable. The universe is smooth and even. Of course it is. But think about it for a moment longer, the way the physicists did, and it becomes deeply strange. 2 regions on opposite sides of the sky are extraordinarily far apart. They are so far apart that, in the entire history of the universe, light has never had time to travel from one to the other. And nothing travels faster than light. This means those 2 regions have never been in contact. They have never exchanged heat, never influenced each other in any way, never had any chance to settle into the same temperature. They are like 2 cups of coffee in 2 separate houses on opposite sides of a country that have never been near each other and never will be, and yet are found to be at exactly the same temperature down to the smallest fraction of a degree. How? If they never touched, how did they come to match so perfectly? This is called the horizon problem, and it troubled cosmologists for years. The simple Big Bang offered no answer. It simply had to assume the universe started out smooth, which felt like cheating. There was a second puzzle too, equally nagging, called the flatness problem. When you measure the overall geometry of the universe, its large-scale shape, you find that it is extraordinarily flat. Not flat like a pancake, but flat in a deeper mathematical sense, meaning that space on the largest scales is not noticeably curved. Now, according to the equations, a universe that starts out even slightly curved should grow more and more curved over time, the curvature amplifying as the universe ages, the way a tiny error at the start of a long journey grows into a huge one by the end. For the universe to be as flat as we measure it now, after nearly 14 billion years, it would have had to start out flat to a precision so extreme that it seems absurd to have happened by chance. It is as though you found a pencil that had been balanced perfectly on its sharpened tip for 14 billion years without falling. You would not say it got lucky. You would suspect that something was holding it there. The simple Big Bang had no such something. And then, in 1979 and 1980, a young American physicist named Alan Guth, born in 1947, working late and worrying over exactly these problems, had an idea that would solve both of them at a single stroke and would change cosmology forever. The idea is called inflation, and I want to walk you through it slowly because it is subtle, and it is one of the most important pieces of the modern picture. Guth proposed that in the very, very first instant of the universe's existence, in a fraction of a second so tiny, it defies imagination. Far less than a trillionth of a second, the universe underwent a period of breathtakingly fast expansion. Not the gentle, steady expansion we see today, but an explosive, exponential ballooning, in which the universe doubled in size and doubled again and again and again, dozens of times over, in an almost incomprehensibly short span of time. A region smaller than a single atom was stretched in that flicker, to something larger than a grapefruit. And the principle continued so that what became our entire observable universe grew from something unthinkably tiny. Then, just as suddenly, this furious inflation ended, and the universe settled into the slower, statelier expansion that has continued ever since. Now watch how elegantly this solves both puzzles. The horizon problem, first. Before inflation, the tiny patch that would become our entire visible universe was so small that all of it was in close contact. Every part of it could touch every other part, could exchange heat, could settle into a uniform temperature. The way a small cup of soup will even itself out to one temperature if you give it a moment. And then inflation took that tiny, already evened out patch and blew it up to an enormous size. Far larger than we can see, faster than light could keep up with. The regions that are now on opposite sides of our sky, regions that seem never to have been in contact, were in contact, long ago, when they were squeezed together in that initial speck. They matched temperatures then, while they were neighbors, and inflation simply carried them apart afterward. Of course, they are the same temperature. They were once side by side, and the flatness problem dissolves just as neatly. Take any curved surface, no matter how curved, and stretch it enormously, and the patch you are standing on will look flat. You live on a curved planet, a great ball of rock, and yet the ground beneath your feet looks perfectly flat to you, because you are so small compared to the whole sphere. Inflation did the same thing to the universe. Whatever curvature it started with, the staggering expansion of inflation stretched our local patch so vast that any curvature was flattened out beyond our ability to detect it. The pencil balanced on its tip for 14 billion years was not luck after all. Inflation was the hand that smoothed everything flat. And inflation does one more thing, perhaps the most wonderful thing of all, which ties the very largest structures in the universe to the very smallest. In the world of the very small, the quantum world, nothing is ever perfectly still or perfectly smooth. There is always a faint, restless jitter, tiny random fluctuations bubbling up and dying away, an unavoidable fuzziness woven into the fabric of things at the smallest scales. Before inflation, when the entire observable universe was smaller than an atom, these tiny quantum jitters were present, microscopic ripples in the density of that initial speck. And then inflation took hold and stretched everything enormously. And in doing so, it stretched those microscopic ripples too, blowing them up from impossibly small to cosmically large, freezing them into the fabric of the expanding universe. Those stretched out ripples became slightly denser and slightly thinner regions spread across the whole cosmos. And over the billions of years that followed, gravity went patiently to work on them, pulling more matter into the denser regions and leaving the thinner regions emptier, until the dense spots had gathered themselves into galaxies and clusters of galaxies, and the thin spots had become the vast, empty voids between them. Which means that the galaxies, the great glowing islands of stars, including our own, including the one your sun belongs to, may have grown from quantum fluctuations no bigger than the smallest things that exist, stretched to the size of the heavens by inflation. The largest structures we know were seeded by the smallest. That is the kind of connection that, once you really feel it, is hard to forget. Inflation is a beautiful idea, and the evidence for it is genuinely strong, because it makes predictions about the tiny ripples in the cosmic microwave background that have been confirmed with great precision. But I want to be honest with you, in the spirit of this whole episode, which is about confusion as much as clarity. Inflation is not a settled, finished, proven fact in the way that the expansion of the universe is. We do not know exactly what drove it. We do not have a complete and agreed theory of what the inflating substance was, or why inflation began, or why it stopped when it did. There are competing versions, and there are respected physicists who have doubts about the whole framework. Inflation is the leading idea, supported by good evidence, and it is part of the standard modern picture. But it sits a little closer to the edge of what we know, in that misty region where the confident facts shade into ongoing research. I tell you this not to unsettle you, but because honesty about the edges of our knowledge is, to me, far more beautiful than a false tidiness. And now we arrive at the deepest confusion of all, the one that the name Big Bang causes more than any other, and the one I most want to set right tonight. People hear Big Bang, and they imagine a moment of creation, a single instant when the universe sprang from nothing, a definite first second that we understand and can describe. They imagine that science can tell them what happened at the very beginning, at time zero, at the first tick of the clock. And here is the gentle, humbling truth. It cannot. Not yet. And perhaps not ever in the way the question imagines. Let me explain carefully, because this is where it matters most to go slowly. When we run the film of the expanding universe backward, the universe gets smaller, hotter, and denser. We understand this very well for an enormous span of cosmic history. We can describe with great confidence what was happening 1 second after the beginning, when the universe was a searing plasma of particles. We can describe the first few minutes, when the lightest elements were being forged, exactly as Gamow and his colleagues calculated. And the predicted amounts of hydrogen and helium match what we actually observed to remarkable accuracy. We can describe 380,000 years after the beginning, when the universe had cooled enough for atoms to form and the cosmic microwave background was released. Our understanding of all of this is detailed and well tested. It is genuinely one of the triumphs of human thought. But keep winding the film backward, past that first second, toward the very beginning, and we reach a wall. As we approach what we call time zero, the equations that have served us so faithfully begin to misbehave. The density does not just get very large. It heads toward infinity. The temperature heads toward infinity. The whole universe heads toward being squeezed into a single point of zero size and infinite density. And in physics, when your equations start producing infinities, that is not a discovery. It is a warning. It is the equations telling you that they have been pushed beyond the range where they work. The way a map of your city is useless if you try to use it to navigate the surface of the sun. That point of infinite density is called a singularity, and it is not really a thing that we believe physically happened. It is a sign that our current theory of gravity, Einstein's general relativity, the very theory that gave us the expanding universe in the first place, has reached its limit and broken down. Here is why it breaks down, in plain terms. General relativity is the theory of the very large, of gravity and space and time on grand scales. It is magnificent at describing planets, stars, galaxies, and the expansion of the cosmos. But it knows nothing about the world of the very small, the realm of atoms and particles, which is governed by an entirely different and equally well-tested theory, quantum mechanics. For almost the whole history of the universe, these two realms stay politely separate. Gravity rules the large, quantum mechanics rules the small, and they rarely have to speak to each other. But at the very beginning, when the entire universe was squeezed smaller than an atom, the very large and the very small become the same thing. The whole cosmos becomes a quantum object. And to describe that, you would need a theory that combines gravity and quantum mechanics into one. A theory of quantum gravity. And here is the honest, humbling fact. We do not have one. Physicists have been searching for a complete theory of quantum gravity for the better part of a century. And despite brilliant attempts, with names like string theory and loop quantum gravity, we do not yet have a finished, tested answer. I want to dwell on this gently, because the idea that a theory breaks down can sound like a failure, and it is not. It is one of the most honest and grown-up things in all of science. Every theory we have ever made is a map, and every map has edges. The map of your country is wonderfully accurate for finding your way between cities, but it tells you nothing useful about the inside of a single atom. And that is not a flaw in the map. It is simply outside what the map was made for. General relativity is a magnificent map of gravity and space and time on large scales, tested again and again, never once found wanting within its proper territory. But the very beginning of the universe lies outside that territory, in a place where the large and the small collapse into one another. And there the map runs out. The infinities that appear as we approach time zero are the map's way of saying very clearly, here I end. To go further, we would need a new and larger map, one that holds both gravity and the quantum world together at once. The search for that map is, perhaps, the greatest unfinished task in all of physics. Many of the most brilliant people alive have spent their whole careers on it, and it is not finished. So when I tell you that we do not know what happened at the first instant, I am not describing a small gap that will surely be filled next year. I am telling you about a genuine frontier, a real and present edge of human understanding, and you are alive at a time when it has not yet been crossed. So when someone asks, with perfect reasonableness, what happened at the very first instant, at time zero itself, the honest scientific answer is that we do not know. We do not have the tools. The Big Bang Theory is not a theory of the moment of creation. That is the great misunderstanding. The Big Bang Theory is a theory of what happened after, of the expansion and cooling and evolution of the universe from an extremely hot, dense early state onward. It is extraordinarily successful at that. But it does not and cannot, with our present knowledge, describe time zero itself. The supposed moment of creation is not a fact that science has established. It is a question mark, a beautiful, open question mark, sitting right at the edge of everything we know. And this leads to the question that children ask and that physicists are still humble before. What came before the Big Bang? What was there first? And here the confusion deepens in a way that is genuinely subtle. So let me try to be very gentle and very clear. In Einstein's picture, and in much of modern cosmology, time itself is woven together with space. They are not separate. They are two aspects of one fabric, which we call space-time. And if the beginning of the universe is also the beginning of space-time, then it may be the beginning of time itself, in which case the word before has nothing to refer to. Asking what came before the beginning of time may be like asking what is north of the North Pole. You can say the words, the sentence is grammatically fine, but there is no place that the words point to. There is no further north. Once you are standing at the North Pole, every direction you face is south. In the same way, once you are at the beginning of time, there may simply be no before. I want to be careful and honest here, because this is contested ground. Some physicists are quite comfortable saying that time began with the universe, and that the question of before is meaningless. Others suspect that our universe may have emerged from something prior, some earlier state or larger structure. and that before may have a meaning after all, one we cannot yet grasp. There are serious, thoughtful ideas about universes that bounce, contracting and then expanding, or about our universe budding off from a vaster cosmos. None of these is established. None of these is more than a careful hypothesis at the frontier. The truth, the deeply honest truth, is that we do not know whether the question what came before even makes sense, let alone what its answer might be. And I find that not frustrating, but rather wonderful. There is still a real mystery here, a genuine unknown, sitting at the foundation of all existence, and no amount of cleverness has dissolved it yet. So let me gather up what we actually do know, and hold it up to the light, because amid all this uncertainty, there is a vast amount of solid, beautiful, hard-won understanding. And I do not want the mysteries at the edges to make you forget the firm ground in the middle. We know the universe is expanding, and we know it with great confidence, from the red shifts of countless galaxies measured over a century. We know that running this expansion backward leads to a hot, dense, early state, and we can describe that state in detail from a tiny fraction of a second onward. We know the universe forged its first light elements, hydrogen and helium, in its first few minutes, and the amounts we predict match the amounts we observe. We know that about 380,000 years after the beginning, the universe cooled enough for the first atoms to form, releasing the cosmic microwave background, which we detect today, filling the entire sky at 2.7 degrees above absolute zero. And we know the age of the universe with remarkable precision. From the cosmic microwave background, measured by a succession of ever more sensitive satellites, we have learned that the universe is about 13.8 billion years old. Not roughly, not vaguely. 13.8 billion years, give or take a small amount. That is a number human beings have measured, from a faint glow in the sky, about the age of all things. Sit with that number for a moment, because of all the things we have spoken of tonight, it may be the one that should astonish you most. And yet, it is so easily passed over. 13.8 billion years. The age of the universe, measured by human beings, to a precision of better than 1%. Think of what that means. A creature that lives, at most, 100 years or so, on a small planet circling an ordinary star in an ordinary galaxy, has worked out, from a faint glow falling on its instruments, how long the entire universe has existed, and has done it so carefully that the uncertainty is smaller than 1/100th of the answer. We did not guess it. We did not assume it from old stories. We measured it, the way you might measure the length of a table. Except the table is all of time, and the ruler was built from the cooled light of the beginning. There is no human alive who would have believed this possible a few hundred years ago. And it was done not by one genius in a single flash of insight, but by thousands of patient people across many lifetimes, each adding a careful measurement, each checking the others, each refusing to be satisfied until the numbers agreed. That is what knowledge really is. Not certainty handed down, but understanding slowly built, measurement upon measurement, until something as vast as the age of the universe becomes simply a number we know. Let that be a comfort as you lie there. We are a young and small and easily confused kind of creature, and yet, working together and very patiently, we have managed to learn the age of everything. Let me tell you a little about how that glow was studied, because it is a story of patience, rewarded. After Penzias and Wilson found the cosmic microwave background in 1965, scientists wanted to study it in far greater detail, to read the fine print written in that ancient light. In 1989, the United States Space Agency launched a satellite called the Cosmic Background Explorer, known by its initials as COBE. Led by scientists including John Mather and George Smoot, COBE did two extraordinary things. First, it measured the spectrum of the background glow with such precision that it matched, almost perfectly, the glow expected from a cooling furnace, exactly as the Big Bang predicted, one of the most perfect agreements between theory and measurement in all of physics. And second, in 1992, COBE detected something subtle and profound. The glow was not perfectly smooth after all. There were faint ripples in it, tiny variations in temperature from place to place, differences of just a few parts in 100,000. Those ripples were the seeds. They were the slightly denser regions in the early universe that, over billions of years, would pull themselves together under gravity to form galaxies, stars, planets, and eventually us. When that ripple map was revealed, George Smoot famously described it, with some emotion, as like seeing the face of the beginning. Mather and Smoot were awarded the Nobel Prize for this work in 2006. It is worth pausing on how strange and how tender that result really is. Those faint ripples that COBE found, those differences of just a few parts in 100,000, are almost nothing at all. If you imagine the early universe as a perfectly still pond, these were the very faintest stirrings on its surface. Ripples so slight, you would never feel them pass beneath your hand. And yet, every galaxy that exists, every star, every world, every living thing, grew out of those barely there ripples. The slightly denser patches pulled in a little more matter with their gravity, and having drawn in more matter, they pulled in more still, slowly, over hundreds of millions of years, gathering and thickening until they became the bright knots and glowing threads of the cosmos we see today. The faintest unevenness in that early glow became, in the fullness of time, simply everything. Picture a wide field of fresh snow that looks, from a distance, perfectly flat and smooth. Come closer and you find it is not smooth at all. There are tiny dips and rises in it, places where the snow lies a fraction deeper, places where the wind has scoured it a little thinner. Now imagine that, given an almost unimaginable stretch of time, those tiny differences slowly deepened, the low places drawing in more snow and the high places shedding it, until the smooth field had folded itself into hills and valleys and great soft drifts. That is something close to what the universe did with its first faint unevenness, except that the drifts it built were galaxies. And you are lying here tonight inside one of them, on a small world that gathered itself out of one of those slightly fuller patches in the ancient glow. It is worth lingering on those ripples, because the story of how they became us is quietly astonishing. The variations COBE found were almost absurdly faint. Differences of a few parts in 100,000, which is like the difference between a perfectly still pond and a pond with ripples so small you would need the most delicate instrument imaginable even to notice them. And yet, those tiny differences were everything. In the regions that were just slightly denser than average, gravity had just a little more to pull on. So those regions drew in matter from their surroundings, growing denser still, which gave them even more gravity, which let them pull in even more matter. It was a slow, patient runaway, unfolding over hundreds of millions and then billions of years. The slightly dense regions became clouds, the clouds became the first stars and the first galaxies, and the galaxies gathered into groups and clusters. Meanwhile, the slightly thin regions gave up their matter to their denser neighbors and grew emptier and emptier, becoming the enormous voids that make up most of the volume of the universe today. If you could pull far enough back to see the whole universe at once, you would find that the galaxies are not scattered randomly like sand thrown across a floor. They are arranged in a vast, delicate structure, a network of glowing filaments and sheets surrounding great, dark, empty bubbles, looking for all the world like a cosmic spider's web, or like the foam on top of a freshly poured drink, or like the branching threads of a nervous system. Astronomers call it the cosmic web, and it is the largest pattern that exists anywhere. And every strand of it, every glowing filament threaded with thousands of galaxies, grew from those faint whispers of difference printed on the cosmic microwave background. The seeds that were themselves, very likely, the stretched-out quantum jitters of the first instant. From the smallest fluctuations to the grandest structure in existence, in one long, unbroken story. You are a small, bright knot in that web, lying in your bed, made of matter that long ago gathered itself out of one of those slightly denser regions. And you are old enough now, as a species, to look back and understand how it happened. Hold that thought for a moment, because it is an easy one to read straight past. The pattern you are a part of, the cosmic web, is the largest arrangement of anything that exists anywhere. And it was drawn by the smallest differences that have ever been measured. There is a kind of symmetry in that which I find very quietly beautiful. The very biggest thing and the very smallest thing turn out to be the same thing, seen at the beginning and seen now, the faint early whisper grown into the vast and glowing lace of the heavens. You do not need to hold all of it in your mind at once. You only need to let it settle, the way fine silt settles through still water, until the sense of it comes to rest somewhere beneath thought. And you feel, without quite reasoning your way there, how gently and how patiently everything around you came to be. After Kobe came even sharper eyes. A satellite called the Wilkinson Microwave Anisotropy Probe, named in honor of David Wilkinson, that same Princeton physicist who had been preparing to search for the background glow when Penzias and Wilson found it first, mapped the ripples in far finer detail in the 2000s. And then a European satellite called Planck, launched in 2009 and reporting its results in the years after, mapped the ancient glow with such exquisite precision that it pinned down the basic properties of the entire universe. It is from Planck, above all, that we get our best value for the age of the cosmos and for what the universe is actually made of. And what it is made of is, frankly, humbling. Here is the inventory of the universe, as best we can measure it, and it is one of the strangest facts in all of science. Everything you have ever seen or touched, every star, every planet, every living thing, every atom in your body and in the walls around you, all the ordinary matter in all the galaxies, adds up to only about 5% of the universe. 5%. The rest is in forms we cannot see and barely understand. About 27% is something we call dark matter, a kind of matter that has mass and pulls on things with gravity, but does not give off or absorb light. So it is invisible to every telescope, detectable only by its gravitational tug on the things we can see. We do not know what it is made of. The story of how we even came to suspect dark matter is worth a moment, because it is a fine example of the universe refusing to add up and forcing us to admit that something was missing. Back in the 1930s, a sharp-tongued and brilliant astronomer named Fritz Zwicky, working in California, studied a great cluster of galaxies and measured how fast the galaxies within it were moving. And he found that they were moving far too fast. They were whirling around so quickly that the gravity of all the visible matter in the cluster, all the stars and gas he could actually see, should not have been nearly enough to hold them together. By rights, the cluster should have flung itself apart long ago. Something unseen, something with a great deal of mass, must have been holding it together with its gravity. Zwicky called it dark matter, and for decades his finding was largely set aside as a curiosity. Then, in the 1970s, an astronomer named Vera Rubin, working with her colleague Kent Ford, made careful measurements of how stars move within individual spiral galaxies, our own kind of galaxy. And she found the same impossible thing, more clearly than anyone before her. The stars at the outer edges of these galaxies were orbiting far too fast for the visible matter to hold them. According to the gravity of the stars and gas she could see, the outer stars should have been flung off into space long ago. Yet there they were, orbiting steadily. The only explanation that held together was that each galaxy is wrapped in a vast, invisible cloud of dark matter, far larger and more massive than the bright, visible part, an unseen halo whose gravity holds everything in place. Vera Rubin's careful, patient work turned dark matter from a curiosity into something the whole field had to take seriously. We still do not know what it is. But we know it is there, because without it, the galaxies would not hold together, and they plainly do. And the remaining 68% or so is even stranger, something we call dark energy, a mysterious property of space itself that is causing the expansion of the universe to speed up rather than slow down. A discovery made in the late 1990s that astonished everyone who expected gravity to be gradually putting the brakes on the expansion. That discovery deserves a few words of its own because of how completely it overturned what everyone expected. For most of the 20th century, cosmologists assumed the expansion of the universe must be slowing down. It seemed obvious. Gravity pulls things together, and every galaxy pulls on every other. So over time, that mutual pull should be gradually slowing the great expansion, like a ball thrown upward, slowing as it rises. The only real question, people thought, was whether gravity would eventually win and pull everything back together, or whether the expansion would coast on forever, ever slower. So in the late 1990s, two competing teams of astronomers set out to measure how much the expansion was slowing by studying the light of certain exploding stars called supernovae in very distant galaxies. These particular supernovae are useful because they all explode with very nearly the same true brightness. So by comparing how bright they truly are with how dim they appear, astronomers can measure their distances with great care, much as Leavitt's pulsing stars once let Hubble measure his. Both teams expected to find the expansion slowing. Instead, to their astonishment, they found the opposite. The distant supernovae were dimmer and therefore farther away than they should have been if the expansion had been slowing. The expansion was not slowing at all. It was speeding up. Something was pushing the universe apart, overwhelming the pull of gravity on the largest scales, accelerating the swelling of space. That something is what we now call dark energy. And its discovery, announced in 1998, was so unexpected and so well established that it earned a Nobel Prize. We still have almost no idea what it is. It is quite possibly related to that very cosmological constant Einstein once added and then regretted, the term he called his great blunder, which may turn out not to have been a blunder at all, but a glimpse of something real that he never lived to understand. We do not know what dark energy is either. So when we say we understand the universe, we must say it humbly. We understand a great deal about the 5% we can see, and we are profoundly in the dark about the other 95%. The honest cosmologist is a person comfortable with a great deal of not knowing. And there are more open questions, more loose threads, even within the firm ground. In recent years, astronomers have found a genuine puzzle in the rate of the expansion itself. When they measure how fast the universe is expanding today by looking at relatively nearby galaxies and stars, they get one value: When they calculate how fast it should be expanding today based on the cosmic microwave background and the physics of the early universe, they get a slightly different value. The two numbers should agree. They stubbornly do not by a small but persistent margin. This disagreement is called the Hubble tension, and it has become one of the liveliest puzzles in modern cosmology. It may be a sign that one of our measurements has a hidden error somewhere, or it may be a hint that there is something missing in our picture of the universe, some new physics we have not yet discovered, hiding in that small gap between the numbers. Nobody yet knows. And so even the expansion that started this whole story, the very thing Hubble measured in 1929, still holds a mystery that the sharpest minds alive have not resolved. I want you to notice something. As your eyes grow heavier and the room grows softer around you, notice how this entire grand story is built from very small, very human acts. A careful man named Slifer, spreading starlight into colors night after night in a cold dome in Arizona. A young mathematician named Friedman, following the equations honestly even when they led somewhere unwelcome, and dying before he could be proved right. A priest named Lemaitre, daring to imagine a universe with a beginning, and insisting that his physics be judged as physics. A woman named Leavitt, sitting at a desk with photographic plates, paid almost nothing, handing astronomy the ruler it would use to measure the cosmos. Hubble and Humason, the famous astronomer and the former mule driver, measuring galaxy after galaxy together. Two men in New Jersey, scrubbing pigeon droppings out of an antenna, never imagining they were cleaning the lens through which we would see the dawn of time. None of them saw the whole picture. Each of them added a single small piece, often without recognition, often without reward. And out of all those small pieces, across a single century, the human species assembled an understanding of the origin of everything. That seems to me one of the quietly miraculous things our kind has ever done. And here is a thought to rest on as we begin to wind down. That ancient glow, the cosmic microwave background, the afterglow of the beginning, is not somewhere far away. It is not a distant thing you would have to travel to find. It is here, right now, in the room where you are lying. That 13.8 billion-year-old light is passing through you. It is falling on the roof above you and soaking through the walls and drifting through the air and passing gently through your own body, through your hands and your chest and your closed eyes. A faint warmth left over from the birth of the universe, arriving everywhere, all the time, in total silence. You are, at this very moment, bathed in the light of the beginning. You always have been. You always will be. It is the most ancient thing there is, and it is touching you now as softly as anything could. So let the strangeness of it settle over you like a blanket. There is no center to the universe, and so there is no center you are far from. The expansion is happening everywhere, including in the space between the atoms of your own body, in the tiniest way, carrying everything gently apart over unimaginable stretches of time. You are not watching the universe from the outside. You are inside it, made of it, woven from the same hydrogen that formed in those first few minutes, hydrogen that has been part of stars and clouds and oceans and is now, briefly, arranged into you. Lying here, breathing slowly, listening to a quiet voice tell an old story about how it all began. There is so much we do not know. We do not know what happened at the very first instant. We do not know what dark matter is, or dark energy, or whether the word before even means anything. We do not have the theory that would let us peer all the way back to time zero. And somehow, that is comforting rather than frightening. It means the universe is still larger than our understanding of it. It means there are still real mysteries, genuine unknowns, sitting quietly at the foundation of everything. Waiting, perhaps, for someone not yet born to begin to unravel them. Maybe someone like the child who looked up at the night sky and asked a question that no grown-up could answer. The story is not finished. It has only reached as far as we have managed to walk, and the road continues on into the dark, gentle and patient and very long. For now, though, there is nothing more for you to do. You have followed the whole arc of it tonight, from the smudges of light that turned out to be galaxies, to the red shifts that revealed the expansion, to the priest who imagined the beginning, to the faint glow that proved it, to the deep and honest unknowns that remain. You have held the whole of it, gently, and now you can set it down. The galaxies will keep drifting apart whether or not you watch them. The ancient light will keep falling, warm and silent, whether or not you are awake to feel it. Nothing depends on you staying with it any longer. So let your breathing slow. Let the small muscles around your eyes loosen. Let your jaw soften, and your shoulders and your hands. Feel the weight of your body sinking into whatever is holding you. The mattress, the cushions, the warm, familiar shape of your own bed. There is no center to the universe, and yet here, tonight, this small, quiet room is the only place you need to be. The light of the beginning is passing through you, as it always has. The universe is 13.8 billion years old, and it has waited all that time to arrive at this single, ordinary, peaceful moment, with you here, drifting gently towards sleep. Let it carry you the rest of the way. Rest now. There is all the time in the world.